let's begin. Some announcements, as always. There's a homework that's due today. Hopefully, you've started. If not, you still have about a little less than 12 hours. Might be a good time to start after class. Do use Canvas for discussion because there were a lot of questions that were answered on Canvas, and probably if you have some question, your answer is already there. So do check it out. The other thing that's due today is also the first milestone for the project. Many of you have already finished that. It's super simple. Maybe one of you can tell me, but my estimate is it takes no more than 15-20 minutes to get it done. Is that reasonable? So yeah, so you just get it done. It's like a administrative thing that's going to make life easier going ahead. And just so that you don't have a day of the week without any homeworks, homework 3 will be available tomorrow. It's going to be entirely on Canvas, so there'll be no programming. It's going to be multiple choice with possibly more than one answer right, and you lose points. No, yeah, with possibly more than one answer right, and it will cover everything that we've done in the semester so far. The idea is it is some sort of it's a way for you to kind of prepare yourself or go revisit everything we've seen in the semester so that you get ready for the midterm, which is in class on the 2nd of March, which will cover everything that we'll do till the 23rd. That's next Thursday. I'm just going to list all the announcements, and then we'll get to questions from you all. By popular demand, there will be extra office hours on Friday. This one is different from the usual. The Friday office hours are going to be only on Zoom, and it's going to be by appointment only, and each block will be 15 minutes long. So there are basically 4 people who can meet a TA on Friday, and you need to kind of, if you want to schedule it soon, if you want to be one of those 4 people this week or whichever week, you need to get on Canvas and put your name down. There'll be an announcement about the mechanics of how this will work, maybe after class today. And this is essentially for those of you who cannot make it to any of the other office hours. My suggestion would be, if you can make it to other office hours, please do. And this can be left as a backup for if you cannot attend any of them. All right, I have gone through all my announcements. Any questions from you about anything? Yeah, so there's a question, will homework 3 be timed or will there be multiple attempts? It will not be timed. I hope it's not timed. I think it's set up not to be timed. There will be multiple attempts. You'll have 2 attempts and the highest score will be taken. And at the end of the first attempt, you will know which questions you got wrong, but not what the right answer is, because then what's the point? Yes.
So does homework 3 is a format of that locally mirrored to the term?
A bit of it. So the midterm is in class, so I can ask you to do more complicated things that I cannot get Canvas to comply. So I can ask you to prove things. There will be at least some part of the homework some part of the midterm that will look like homework 3. Is that other questions about homework 3, homework 2, midterm, project, the extra office hours? Yes.
Yeah, I've been having an issue with my perceptron, but
Okay.
I hope other people are having the same issue. But basically, the learning rate, I'm putting the learning rate of 1 and the learning rate of 1 and 10 exact same values, and I don't know if that's something wrong with what I have written or if that's something that happened.
Did you initialize your weights to 0?
No.
So let's wait. You said 1 and what? What else?
1 and 0.1.
Okay. Here's a sanity check. What if you change your learning rate to a massive number, like 1 million? See what happens. Essentially, to see if your learning rate has any effect on your code. Or change it to a negligible number, almost 0. See what happens. What is definitely possible is there are different hyperparameters that behave similarly or even identically. That is completely possible. But what is almost impossible is all hyperparameters values behave the same way. Do other people see such behavior though? Yes.
Yeah, on the system, we do see that behavior like, I checked it with different learning rates, on different learning rates, I'm getting different activities, but for one and one of them.
Okay, it is completely a plausible situation. Usually what I find is different hyperparameters, especially things like learning rate and other such parameters that control how fast the optimization happens. You get behavior that looks like this. Imagine I'm plotting the learning rate on this axis, and I'm plotting the cross-validation accuracy here. What you might notice is that for some values, it kind of goes up and then it goes down. And there's going to be some region here where it's basically similar. And you could even plot this in the log scale to get a sense of whether it moves too fast or not. I see there's a question on Zoom. I'll go to that and then come back to the in-person question. For section 2, part 1b, where we have to count functions of the form xi implies xj, are the variables allowed to be negated, or are we assuming monotone implications? I would say two answers to that. First one, assume monotone implications. Just write your assumption in the homework. Second, we only care about the order of magnitude. So you can even give us the answer in the big O notation, and that will be fine. Or if not, if your order of magnitude is right, it will be fine. And if you do not make that assumption, you can. Oh, I see that Aman has already answered this question. I'm wasting my breath here, but it's for everyone else also. If you do not want to give an answer in the big O notation, your answer should agree with your assumption. So there are only two assumptions here. All variables no variable can be negated. So you have xi, xj, xi implies xj, or another one is negations are allowed. So you might have something like xi implies not xj, or not xi implies xj, and so on. These are the only two worlds you can be in. My suggestion is make an assumption that variables are not negated. That's totally fine. And if you've already solved it and if you've already written it up, just with the other assumption, make sure that you mention it somewhere. I saw some other hand. Yeah. They're not. No, they're not. Otherwise, it becomes kind of boring. Yes. It will not be a proof we've covered before. I've not written the midterm yet, so I'm still making it up. But it might be a proof that is kind of based on similar principles as what we have seen in class. So it could be nearly isomorphic, but not identical to something we've seen in class. I don't like the idea of asking a proof that we've already covered in class, because then what's the fun? It's like solving a puzzle. I mean, what's the fun in solving a puzzle if you've already done it? It's easy, sure. Yeah, that is an answer. Yes.
For those proof, that's proof that we are likely going to have on the midterm. How rigorous we need to be? Because there's like continuing by closure and saying every single principle we use, like when we reorder condition with
it can be as rigorous or as non-rigorous as I show in the slides. There are some things that you can kind of elide because we all agree that, for example, 1 is greater than 0. So I don't want you to prove it. I don't want you to spend 500 pages proving that 1 + 1 is 2. Someone already did that. But at the same time, I don't want you to say the proof of this is obvious and I'm done. Don't be like Fermat from his last theorem, where the margin, you know the story? Yeah. So somewhere in between, I would say kind of use the level of rigor that we have in the class. Other questions? Yes, there's a question on, will the midterm include programming? Definitely not, because it's going to be on paper. And I dread the idea of compiling paper code. So homework 1 grade, the question, when will we see our homework 1 grades before submitting homework 2? Unfortunately, it's not close to being graded. It's in the process. So yeah, I'm hoping my TAs are they're avoiding looking at me now. But I'm hoping that homework 1 will get graded sometime next week. Yes. Yes. So the question was, when we're reporting number of perceptron updates, is that over all epochs? It is over all epochs. Essentially, what I want is, how many times has your perceptron weight changed over the course of learning?
Another question, it asks us to report development and accuracy. In the code, we are.
Go on, speak up.
So in the code, we are reporting development set accuracy after each.
Yes.
In our type report, do you also want that, or do you only want us to say what the best?
I think it's the best one, right? Do you remember? Yeah, so it's the best one. Yeah.
Print all the accuracies for all the different ones. Yeah, but that's just in the code.
Further questions on Zoom. Will both homeworks be graded before the midterm, or can we get the solutions for the theory parts of the homework before the midterm? For sure, you'll get the solutions for the theory parts before the midterm. Both homeworks being graded before the midterm, I think definitely one will be. Two, I hope, but it's going to be close. But I'll make sure that you have access to all the solutions for the theory parts before the midterm, with some sufficient time so that you can actually go over it and you can ask questions about it and such things. Yes.
Final grades in the test development does it follow a structure, or is it very random after each epoch?
So are you asking, after each epoch, will the accuracy have any structure? It tends to go up. So what you might notice is that it tends to go up, and after a certain point, it kind of it may start falling or flattening because it's overfitting. It's not random. It's not going to be random. So just so that I understand the question, you're asking, is there a pattern to the development set accuracy as learning proceeds? Is that the question? The pattern almost often looks like this. If you plot the dev set accuracy, you might see something like this. So this is, let's say, a number of epochs, and let's say this is it looks something like this, which means it goes up, and then after a certain point, it starts going down because it is overfitting. In a perfect world, you might want to even stop learning here, because beyond that, you're overfitting. What you will not see is something like this. You're not training on the dev set, but you might end up it's overfitting the training set. That's why the dev set accuracy drops. The dev set is not seen. So the dev set is not, the development set is unseen, whereas the model might end up overfitting on the training data. And as a result, it's memorizing the training data a little too well and underperforming on unseen examples. Oh, you want to know if there's going to be a pattern for the weights, not for the accuracy.
So
yes.
Whichever weights are good set of weights for dev set, they will at that point, at that epoch, you will have more accuracy.
Sure.
Then
very good question. So I don't know if people followed the question. I'm not going to repeat it, mostly because that's going to be the basis of our discussion for a good part of today and to next week, when we are talking about computational learning theory, where the question is, what kind of assumptions do we have to make to ensure that the development set performance is not too bad and is not too, does not vary too much. So let's come back to that question later. Yes,
For the project, I noticed we don't have a development set.
yes.
Is there a problem with using the test set and development set?
Don't do that. I would say, don't use it. Don't. I would say use cross validation. You don't need a dev set. You can use cross validation to pick whatever properties you want. We did not give you a development set partly because we didn't want to slice the data even further. So don't use the test set as a development set. Because it's just going to, then you'll end up, what happens is eventually, if you do enough number of experiments with hyperparameters and such things, you might end up overfitting your model to the development set using the hyperparameters. And so it might not generalize to future examples because it has seen the dev set a little too often. Okay. If there are no questions, I propose we move on to the technical part of the class. I want to quickly wrap up something that we discussed in the last lecture, namely least mean square regression, just to kind of remind you where we are. We talked about the least mean square objective, which is simply the goal of learning is to minimize over all the weights the sum of squared errors over the data set. And then I spent a bit of time talking about gradient descent, where I derived the gradient of this expression and showed that in every iteration, the idea of gradient descent is very simple. You want to minimize a function. The gradient at any point, you have a current guess for the weights, which means you're somewhere in this, imagine the space of all possible weight vectors. So you're somewhere in that space and you have a current guess. And the gradient at that point tells you which is the direction in which the function, this function, the objective here, is growing the fastest. And gradient descent is simply saying, take a step in the opposite direction. And you keep iterating. And if your steps are reasonably chosen, you'll get to the minimum. The only problem with that was that in order to compute the gradient of this function, you need to iterate over every example because the function itself is a sum over many examples, and the gradient of that objective is simply the sum of all the gradients of these internal things. So you need to iterate over the entire data set to get one update, then iterate again to get one update. And what I mentioned was maybe can we do faster updates? Is it possible that we can instead of iterating over these the entire data set every single time, can we make updates to the weight vector as soon as we see an example, or maybe a small number of them, where we've seen that example, we make an update, and that way we don't have to imagine that you have a very, very bad weight vector. Why bother iterating over the entire data set to collect the gradients? Can we not just quickly make an update so that we move out of this bad weight vector? And that gives us this algorithm that I call incremental or stochastic gradient descent, where learning proceeds in multiple rounds, which very much behaves like the epochs that you're using for your perceptron. And in each epoch, you iterate over all training examples. And for each training example, the sort of mental model I want you to have is pretend that that one training example that you're currently holding is the entirety of the data that you have. That's all the data you have. So you can write down a loss or a cost. The objective for that one example, let's say you're sitting on xi and yi, it's simply this expression here. So this is the objective we want to minimize for this one example. And I can take the gradient of this example with respect to weights. And I talked about how you compute the gradient in the last lecture, so I won't get into the details. And that will give you an update for all the weights for that, for using this example. And now you've used up this example and you move to the next one, and you move to the next one, and you loop over all the examples. Once you finish a loop over the examples, then you loop over all the data again. And every time you see an example, you make an update. This update rule is also called the Woodrow-Hoff rules. And it's today a lot of machine learning algorithms, a lot of times when people use machine learning, they use some version of this kind of a rule where we iterate over a data set, and usually there's a shuffling step here. Just like you have with your perceptron, you shuffle the data, and then you iterate over the training data, pick one or usually a small batch of examples called a mini batch, compute the gradient over that, pretending that that's all the data you have, make an update, and essentially do this again and again. This style of learning was in the neural network literature, it's called the Woodrow-Hoff rule. It used to be called the Woodrow-Hoff, still is, I guess. Once the name is made, it doesn't get taken away. But the generalized version of this is called stochastic gradient descent, which was invented by, I think, Robbins and Munro, or I have to look it up, but around 1955. And it turns out that this style of learning can get to the optimum. The goal is to get to the optimum value of that overall objective. It gets to the optimum much faster than the batch descent because we get quick updates on the data. Any questions? This is where we stop. Yes.
Yeah, so you mentioned like mini batches.
Yes.
So using the mini batch, that's also stochastic.
Yes.
Okay. So
Yeah.
like updating every example versus like a small batch.
Like 10.
Similar.
Yeah, it tends to be a little more stable. It tends to be slightly stable, and is almost, when people use stochastic gradient descent, it's usually the mini batch version. We'll talk a lot about stochastic gradient descent over the course of the semester. In particular, I'll introduce it again and go into a little bit more depth when we visit support vector machines, and possibly also during logistic regression. But it's an idea that's kind of worth letting it kind of sit in your head for a bit, because what I want you to think about is, why should this even work? I mean, this gradient descent works because it has some formal properties that guarantee that it works. Why should this even work? And especially when there's randomness involved. So there's stochasticity in the choice of which point you pick. So just keep this in your head. There's a question. Yes. Yeah, you.
Oh, okay. So is there any assumption of y as a function of x?
The assumption here is that we are assuming that y behaves like W transpose X.
Okay.
But we are not in real life. We don't know what the real y is. There's no assumption about that at all. We are modeling y as a linear function of X.
Okay. So isn't that for any kind of function, you can definitely do this?
Yeah, you can do this. You'll get some weights. Whether it's good or not is a different question. See, the thing is, you have an optimization problem. I'm going to just use this in this optimization problem. Oh, there's already a half. Is well defined. It does not care about whether y, what the true function between y and x is. Now, if it turns out that y and x were linearly related in real life, the minimum value, what will the minimum value be? If it was truly, y was truly a linear function, it will be 0, because you'll get a weight vector that has 0 error. If it was not really a linear function, you will not get a 0. That's pretty much the only thing. Okay, I don't want to spend too much time on this because I spoke about this also in the last lecture, and I kind of gathered that many of you have encountered this in the past. The only other thing I want to discuss is about this quantity here, the learning rate. In general, well, not for the non-separable. There's no notion of separation here. This is a regression. In general, the learning rate for stochastic gradient descent should decrease to 0 as the number of epochs increases. There's a formal version of that statement that we'll encounter later, but this is what you are also doing in your, what did I call it in your homework? Where the learning rate keeps going down. Yeah, where it decays, yes. So the idea there is if your learning rate decays and eventually hits zero when the number of epochs is infinite and satisfies some other properties, then learning will converge to the exact same thing eventually at infinity that your original full gradient descent would have. Otherwise, you'll get to something close. Sometimes the learning rate is also called the step size. And there's an entire cottage industry around how to choose the right learning rate. What you use in your homework might look something like 1/1 plus epoch. It's rather simple, but there are all these fancy learning rate choosing mechanisms that essentially say learning rate for those weights that have been updated a lot should be small, or things like that. And they come with interesting properties. And we'll touch upon some of those much later when we talk about neural networks. The other thing about stochastic gradient descent is if you choose a better starting point, you might converge faster. But keep in mind that you will converge no matter what because you have a convex function. You'll converge eventually no matter what to a good answer because you have a convex function. But if you choose a better place, you'll take fewer steps to get to the right answer. Now you might ask, how do I know what's a better place? And I don't know. I mean, you just get lucky. So the final thing I want to say is the gradient descent and stochastic gradient descent are so simple. They are really easy to implement. At least if you don't want to make it complicated, you can keep it simple. And you already are in your homework. But a whole bunch of algorithms that we will encounter, including, it turns out, the perceptron algorithm, can be seen as special cases of gradient or stochastic gradient descent. So there's like a unifying theme that seems to have emerged over the decades across machine learning, where gradient-based optimization has become like the one powerful tool that we keep using again and again. And this was not always the case. Even as recently as maybe 15 years ago, it was not obvious that this is how it would be. And so there were many other learning algorithms that optimization algorithms that were used in the state of the art. But over time, it seems like the community has converged to gradient-based optimization simply because A, it seems to work, and B, you can take advantage of existing vector libraries and GPUs and such things to make learning really fast. So libraries that you may have heard of, like PyTorch and TensorFlow and such things, are basically stochastic gradient descent plus with a lot of extra hooks and all that. But that was not the topic of our discussion for this unit. It was all about least mean squares. So I want to quickly summarize that part. Linear regression is where we want to predict, or regression in general is where we want to predict a real valued output as a function of the input features. And linear regression in particular is when that real valued output is modeled as a linear function of the input. We talked about learning by minimizing cost or minimizing loss. And we looked at gradient and stochastic gradient descent. It just so happens that for linear regression, the objective we specifically looked at, the least mean square regression, need not have been solved using gradient descent. There is a closed form solution. And as an exercise, I want you to try it out. So here are two exercises. The first one is I talked about this little data set where you can predict the mileage of a car with 4 examples. So try to see how gradient descent and stochastic gradient descent might be applied for that small data set. See if you can implement it or work it out on paper, just to kind of and step through it, just to get a sense of how that objective changes, the objective value changes as gradient descent proceeds, and just the mechanics of it. Another thing is even more interesting. Turns out that if your entire data set could be written in this fashion, every x, you build this big matrix X, capital X, whose columns are the input features, and you build a vector Y, whose rows are the output labels. I could do that, right? Just by stacking together all the features, I can get a big matrix, and I can start to roast the labels together to get a vector. I leave this as an exercise. If you're interested, we can talk about it in office hours or something like that, or I can send you some pointers. But the least mean square objective that we saw before is equivalent to this optimization problem that is written entirely as a sort of a matrix vector expression. And this, it turns out, can be solved analytically by taking the derivative and setting it to 0. And if you do that, you can show that the weight vector is exactly that expression there. I'm not going to talk about how, but try it out. Even if it's painful and you're irritated by it, I encourage you to try it out, mostly to kind of get comfortable with thinking about weight vectors and such things, and taking derivatives of these objects. Any questions? Questions about learning rates and weight vectors and regression in general? If yes,
few variables that is similar plus something less than can also.
well, okay. So the question is, what happens if maybe instead of variables, I'm going to call them features? What happens if two features are very similar and or even identical? How do you handle that? We didn't talk about feature selection at all. There are a few different ways of doing that. If you don't mind, we'll move that discussion to much later in the semester. And it applies not just to regression, but also to classification. If I have the same feature twice, how does that affect your learner? Well, there's no such thing called correct weights. If it gets the right label, why do you care? So there's something to think about there. But I want to kind of avoid the discussion for now, simply because that will take us on a bit of a tangent.